We're now going to derive the kinematic equations. The kinematic equations describe the case where we have constant acceleration. The kinematic equations come up a lot in senior school physics syllabi because the case of constant acceleration comes up a lot because it describes objects falling under the influence of gravity close to the Earth's surface. So for example, this ball is undergoing constant acceleration. So we can derive the kinematic equations just using the acceleration is equal to dv dt, the derivative of the velocity with time, and that the velocity is equal to ds dt, the derivative of the displacement with time. The kinematic equations can be written as v is equal to u plus at, where v here stands for the final velocity, u is the initial velocity, a is the acceleration, which has to be constant, and t is time. The second kinematic equation, s is equal to ut plus a half at squared. S describes the displacement of the final position measured from the first position. So we're assuming that the initial displacement is equal to 0. And the final kinematic equation is v squared equals u squared plus 2as. So let's see how these equations can be derived now.
Okay, so we're starting from acceleration is equal to dv dt. And we know that we've got constant acceleration. Now we can rearrange this equation to be the acceleration times dt is equal to dv. And then we're going to integrate both sides. So we know that at t equals 0, we've got that the velocity is equal to u, and at time t, the velocity is equal to v. So we can now place these limits onto our integral equation. So the time is going from 0 to t, while the speed is going from u to v. Now we will integrate. So we end up with at from 0 to t is equal to v from u to v. And so we have a t minus 0 is equal to v minus u, and so at is equal to v minus u. And so we can rearrange this to have v is equal to u plus at, which is the usual way to write that kinematic equation. Now, this is a vector equation, so we can write it if we want as the vector v is equal to the vector u plus the vector a times t. So to get our next kinematic equation from this, we'll need to use v is equal to ds dt. So once again, we can use the same steps. So we've got v dt is equal to ds, and we're going to say at t equals 0, s is equal to 0, and at t equals t, s is equal to s. So we'll integrate these now, and we're going from 0 to s, and we're going from 0 to t. So the limits on the integral are always related to the thing after the dt, because that's what we're integrating with respect to. Now we've got an expression for the velocity just up here. So we are doing the integral from 0 to t of u plus at dt, which is equal to the integral from 0 to s ds. So now integrating this, we've got ut plus a, and then when we integrate t, we get t squared on 2, and the limits are from 0 to t, and this is equal to s from 0 to s. So we've got ut plus a half at squared is equal to s. So this is our second kinematic equation. We've got s is equal to ut plus a half at squared. And again, these can be vectors. So sometimes we'll use it just in one dimension, but we can also use it in multiple dimensions, in which case S, U, and A are all vectors. Now let's scroll up to give us some space to get our last kinematic equation. So with our last kinematic equation, we don't want to include T in the equation. We want an equation in terms of S, U, and V. So what we can do is take our second kinematic equation here and replace T. So let's use our first kinematic equation. We've got V is equal to U plus AT. We can rearrange this to have T is equal to V minus U on A, and then sub this into star. So what we now have is S is equal to U times V minus U over A plus a half A and then T squared, so that's V minus U over A squared. So this is equal to UV minus U squared on A plus, we've got 2A on the bottom. We've got an A on the top and an A squared on the bottom. So the A on the top cancels one of the A's on the bottom, giving us a 2A on the bottom. And then we've got V squared minus 2UV plus U squared. So that's expanding V minus U all squared. And that's equal to S. Okay, so let's times both sides by 2A. So we've got 2AS is equal to this, we need to times by 2, so we've got 2UV minus 2U squared plus V squared minus 2UV plus U squared. So this cancels this. We've got minus 2U squared plus U squared, so that cancels one of these, so we've just got minus U squared. So this is equal to V squared minus U squared. So this gives us our final kinematic equation, which we can write as V squared equals U squared plus 2AS. Now let's not write this one as vectors because we haven't covered vector multiplication yet, so it's not absolutely clear what we mean by multiplying two vectors together. So we'll just write this one as a one-dimensional case. But obviously, if we had 3 dimensions, if we had this for x, y, and z, it would hold in each of those directions. So in the y direction, we could write vy squared equals uy squared plus 2ay sy, for example. And at the same time, we'd have vx squared equals ux squared plus 2ax sx.